All right, thank you so much for the kind introduction and the invitation to speak with all of you today. I wasn't aware of the EASF forum previously, but I'm very impressed and I think it's great what you guys are doing. So thanks for taking the leadership to put something together like this, and hopefully it keeps growing. So today I'm going to talk about optimization-based design and advanced manufacturing of multi-scale structures. Before I get into the details, I want to acknowledge my amazing collaborators that all contributed to what you're going to see today. So we have Anderson Pereira from PUC-Rio in Brazil, Miguel Aguilo from Morform, Glaucio Paulino, NAE member from Princeton. And since this forum is meant to bring together early career researchers, I want to highlight my collaborator, Fernando Sonora, who just finished his first PhD at PUC-Rio in Brazil and is almost finished with his second PhD here at Georgia Tech. And he's kind of a jack of all trades. He can do mechanics, optimization, high performance computing, machine learning. He's doing additive manufacturing, experimental work. So he can do it all. And hopefully you'll have an opportunity to meet him at some point. But let me talk about our work to design and manufacture optimized structures with spatially varying properties and hierarchical architectures. And what I mean by that is we're looking to optimally design macro scale geometries and at the same time optimally distribute porous anisotropic architected materials within. So here is a part that we designed and manufactured. It's about 14.5 centimeters tall, printed using masked stereolithography 3D printing. And if you look carefully, you'll notice that there are clearly some meso-scale features. And if you look very carefully, you'll notice that those meso-scale features actually vary from point to point within the larger geometry. So if you look here, you can see we have one architected material, and then a transition region to another architected material. And so the goal of today's presentation is to understand how we can design structures like these using topology optimization, and then subsequently how we can manufacture these parts that have a high level of complexity at both the macro and meso scales. So I'm going to start with some basics of topology optimization in case some of you are not so familiar with the field. Before I get into our multi-material and multi-scale approach, and some specific details on lattice-based optimization and manufacturing, and then Spinodal-based optimization and manufacturing. So let's start with some basics of topology optimization. And let's assume that we want to design a structure or a component inside of this serpentine region to efficiently support this load P. Okay, first thing that we need to do is we need to define a mathematical statement of the problem that we want to solve. So today I'm going to focus on maximally stiff structures with limited volume. And so our objective function is compliance, and our constraint here limits the total material volume. Now the design itself is defined through density design variable Z. So at each point in my domain, I'm going to have a density design variable, and these are the things that are going to change as we iteratively move toward an optimized solution. Now, in order to evaluate my objective function, I need to know the response of my system, right? How does this thing deform under the loads? So for that, here we're considering static elasticity, and so the displacement field is essentially my state variable. And I can solve for that using principle of minimum potential energy and so on. Now, to solve this optimization problem, we're going to consider an iterative gradient-based approach where we start with some inputs. So that's going to be our design domain, boundary conditions, initial density field. And then we solve our boundary value problem, typically using finite elements. Next step is to perform a sensitivity analysis, where we take derivatives of our objective and our constraints with respect to the design variables. And so these derivatives tell us how small changes in our design variables are going to influence the objective and the constraints so that we can update our design to improve the objective without violating the constraints. And we do this in an iterative procedure until we meet some convergence criteria. So here you can see the structure coming into view where white is void or no material and black is solid material. Okay, and so this gives you a basic idea of what topology optimization is and roughly how it works. But why is it useful? What is it used for? So it's been used in several fields of engineering. I think maybe the most famous example came from Airbus, where they used topology optimization to design the ribs of an airplane wing in order to reduce weight and ultimately save on fuel. Here's an example in biomedical engineering where they used topology optimization to design patient-specific craniofacial implants for patients with traumatic facial injuries. Here's an example on the smaller scale in material design, where these researchers used topology optimization to design the geometry of architected materials, so the small scale architectures making up a material, in order to achieve a wide range of Poisson's ratio. So geometry is allowing them to control material properties. And then on the much larger scale, topology optimization has also been used in civil engineering to design, for example, lateral bracing systems of tall buildings. So here in this example, you can see a pattern that we often see in our optimized solutions called a Mitchell truss. And this structure was actually constructed in China. Okay, so now let's get into our approach for designing multi-scale structures that, again, have hierarchical architectures and spatially varying properties. Why are we interested in these two types of features? Well, many natural systems take advantage of these features to achieve various functionalities. So for example, here is the cuttle bone, which is the internal porous shell structure of the cuttlefish. It has a layered architecture with some pillars in between that enable it to resist the high compressive pressures experienced in the deep sea. And at the same time, the porosity here enables the cuttlefish to both be lightweight and also to control its buoyancy. So this is an example of hierarchical architectures in a natural system that lead to some functional behavior. In terms of spatially varying properties, there are many examples of biocomposites in natural systems. So here we have the mantis shrimp, which you may know has this sort of dactyl club that strikes its prey with a huge amount of force. And it turns out that biocomposites play a critical role in the mechanics of this system. So in a paper published in Science, these researchers showed that the cross-section of the club is functionally graded in terms of stiffness and hardness. And it turns out that cracks tend to nucleate at the interface between what they call the periodic region and the impact region. And because of the abrupt change in stiffness in the impact region, those cracks are prevented from propagating all the way to the exterior, and so they achieve some damage tolerance. Okay, so this is an example of how spatially varying properties lead to functionality. So now, inspired by these kind of beautiful natural systems, we want to design our optimized parts to mimic some of these features. And so to do that, we're going to adopt multi-material topology optimization. And several years back, we proposed a formulation that can handle an arbitrary number of candidate materials. So previously in the literature, we were limited to around 3 materials. Our formulation can handle as many materials as we need. And this formulation looks very similar to what I showed you before for single material, but a key difference is instead of a single density design variable field, we now have a design variable field for each of our M candidate materials. So for example, if I had 5 candidate materials, at each point in my domain, I have 5 design variables, and the optimization can choose from any of those 5 as we optimize the structure. But how do I get the optimization to choose just a single material at each point? For that, we use material interpolation functions. So just as a reminder, again, we have a density design variable field for each of our M candidate materials. We apply a density filter to those design variable fields. This is a standard procedure in topology optimization that both regularizes the problem and establishes a minimum length scale. But the key here are these two material interpolation functions. So the first one penalizes intermediate densities. So we either want our design variables to take values 0, meaning void, or 1, meaning solid. We don't want anything in between. And so this function makes it inefficient to have intermediate densities in our design. The second interpolation here was inspired by the work of Stegman and Lund in fiber orientation optimization, and it penalizes material mixing. Now we introduced this parameter gamma here that enables us to smoothly transition from the convex case where both intermediate densities and material mixing are okay, to the case where both of those things are penalized. So what you're looking at in this plot here, and in these plots, is the interpolated stiffness in a given element that has two candidate materials. And so you can see at this back corner, 1, 1, where we would have full material mixing, you can see that the stiffness goes to 0. And so it makes it inefficient to have mixing in our design. Now here we're focusing on interpolating the isotropic material parameter Young's modulus, but our formulation can handle a more general class of materials, right? So for example, porous anisotropic architected materials. And in the first portion of this presentation, I'm going to focus on lattice-based architectures that are characterized by a periodic tessellation of some unit cells, okay? To handle architectures like these, we need to account for two things in the optimization. When we compute the volume of our part, of course, we need to account for the fact that these things are porous. So we need to account for their relative density. And then when we compute the stiffness, since these things are no longer isotropic, they're no longer characterized by, just Young's modulus and Poisson's ratio, we're going to interpolate the entire constitutive tensor of the architectures. So we pre-compute a homogenized elasticity tensor of each of our architected materials, and then we interpolate those elasticity tensors to prevent material mixing, okay? So let's regroup a little bit. We saw our formulation. We saw how we can use interpolation functions to both penalize undesirable features in the solution and also to translate our design variables into stiffness properties that allow us to essentially solve for our displacement field. So right now we're here in our algorithm, okay? So we need to compute derivatives and then use those derivatives to update our design. So let's do that. So here we have the sensitivity analysis, and I don't want to go through all the math here. It looks like a lot of math, but really this is simple. We're just doing the chain rule for the objective function, chain rule for the constraint functions. And of course, we can derive expressions for each of these terms, which is what you see here. And the only thing that I want to draw your attention to is each of these terms is a function of things that we already know. So the design variables, the stiffness matrix, the displacements, which we've already computed. And so it's very computationally efficient now to compute our sensitivities. So now that we have our sensitivities, we can use this information to drive our solution toward an optimal, okay? So let's focus first on some lattice examples. I'm going to show you an example of design, and then we'll talk about manufacturing. So first example is a cantilever beam. And so we're going to limit our material volume in this domain to 2.2% of the domain volume. And we're going to allow the optimization to choose from several candidate architectures. So in the top row here, you can see the unit cells characterizing the architected materials that are available. In the second row, we have the directional tensile stiffness. So for example, this plot is indicating that the blue material has high stiffness along the directions of the axes and pretty much no stiffness in any other direction. Whereas, for example, the orange material is basically isotropic, same stiffness in all directions. And then similarly, we have the shear modulus, directional shear modulus at the bottom. So let's take a look at some designs. So first we design for a reference case, so a single solid isotropic material. And we define the objective function value of this structure as F0. Okay, so that's our reference. Then we design for 6 different subsets of our porous anisotropic architected materials. The first thing to notice here is that although all of these structures have exactly the same volume of material, the porous ones tend to be bulkier than the reference, and that makes sense, right? The other thing to notice is that the objective function of the porous structures tends to be larger than that of the reference, so they're not as stiff. And there are a few reasons for that. The main reason is that by limiting our optimization to choose from these specific architectures, we're sort of putting some additional constraints on our problem, right? Each of these architected materials has certain directions of high stiffness and other directions of not so high stiffness. And so the directional stiffness of these architectures dictates the orientation of the members in the final design. Not only that, because these things are porous, we're potentially moving material away from potentially more optimal regions. okay? But let's take a closer look at exactly how these architectures influence both the geometry and the material distribution. And let's focus first on these blue-green type materials that have high stiffness in the X3 direction, or kind of the tensile direction of our beams. And let's notice that these blue and green materials tend to locate themselves where we expect tension and compression in our beams, right? Whereas a material like the yellow one, which is much more isotropic and has high shear stiffness, that material wants to locate itself where we expect inclined members and where we have high shear. Okay, so clearly these architected materials are influencing where the different materials are located in the design, but they also influence the geometry itself. So look at these blue members right here. Remember, the blue material has high stiffness in the X3 direction, the vertical direction. So these members tend to be very vertical. As I move toward the green material, which is a little bit more isotropic, I start to get some inclination in the members. And then as I move to the yellow, which is much more isotropic, that inclination is much more dramatic, okay? So these architectures influence both the material distribution and the geometry of the design. So that's the design part. Now we want to manufacture these architectures that are composed of, these structures that are composed of these architected materials. And I'm going to illustrate our manufacturing capabilities, not with these specific structures, but we've redesigned the cantilever beam for 3 different combinations of architectures that kind of illustrate our capabilities in a little bit better way. But just remember, the difference in these structures is dictated by the mechanical behavior of the architectures that they're composed of, right? So now there are a few challenges in manufacturing structures like these multi-scale structures, right? First challenge is handling the connectivity between different architectures in a transition region, right? And like I said, I have these 3 cases to illustrate different ways that we can handle the connectivity. So in the first case, we have 2 unit cells that have the same geometry, but different bar diameter. So these are guaranteed to be well connected, but may have an abrupt transition. In the second case, we have 2 unit cells that have totally different geometry. And no matter where we try to connect them together, they're not going to be well connected. And then in the third case, we have 2 unit cells that, if connected at their boundaries, they're well connected, but anywhere in between, they're not going to be well connected. And we want to be able to handle all of these types of cases and essentially come up with nice smooth transitions like you see at the bottom, where in the first case, we've done an interpolation on the bar diameter. In the second case, an interpolation on the geometry of the unit cells. And in the third case, we've essentially done, we've generated a set of hybrid unit cells to ensure connectivity. Okay, so we have some way of handling connectivity between different lattice-based architectures. Another challenge here is simply communicating the multiscale geometry to our 3D printer. So this is a complex structure. Then we're going to embed these complex meso-scale features throughout, okay? And if we generate a surface representation or a triangulation of the multiscale structure, it leads to STL files that can be enormously large, especially if we want to scale our macrostructure geometry and keep our mesoscale features kind of at the resolution of the printer. And so we want to avoid surface representations, avoid STL files, and figure out a new way to communicate with our 3D printer. So quick side note, we're focusing here on stereolithography 3D printing, where you essentially cure liquid resin layer by layer using UV light. And we're specifically focusing on the techniques that project or display a pixelated image of an entire layer at once. And so with these approaches, we essentially translate our design into a voxel representation and then project slices of that voxel representation to the underside of our resin vat. So with this voxel-based approach in mind for the printing, we're going to adopt a voxel-based approach to embed our microstructures and communicate with our 3D printer. So our optimization-based design approach gives us essentially a density field that's a mapping between location in our design domain and the meso-architectures of interest. Could be these main 2 meso-architectures or an interpolation between them that enables us to achieve functionally graded transitions. But essentially the idea is we're doing a Boolean intersection of the volumetric topology optimization data and tessellations of our architectures over the design domain. So for example, if you look at a slice through this region of the beam, which you can see here for a structure with an abrupt transition, and here for a structure with a functionally graded transition, the idea is we use this as a mapping. So we pick up a pixel in what I call the macro slice, and that tells us which micro slice to map to. And we essentially replace each pixel in our macro slice with the corresponding pixel of our micro slices, and we end up with these embedded slices that we can send to our 3D printer without any notion of an STL file. And here you can see the critical importance of the functionally graded region, right? In the abrupt transition, we don't have very good connectivity between the different architectures. Whereas when we do the functional grading and the interpolation, now we have a nice, well-connected, smooth interface between the two. So using this approach, we manufactured our 3 cantilever beams. They're each 14.5 centimeters tall. The unit cells have edge length 1.5 millimeters, and the smallest bar diameter that we were able to achieve on our Prusa mass stereolithography 3D printer, just under 200 microns. You can see the 2 different unit cells and the transition between them. Here's the second cantilever beam. Again, a very elegant transition between 2 totally different geometries. And then the third beam, 2 unit cells and the transition between. We've also used the formulation to design and manufacture slightly more complex and slightly larger scale structures. So here we have a hyperbolic paraboloid canopy structure that has a uniformly distributed vertical load applied to the top of the canopy. And the canopy region is fixed to be the geometry of a hyperbolic paraboloid, and it's specified to be composed of this face X blue unit cell. This red region is also a fixed geometry specified to be composed of a solid material. And then we use the optimization to design the supports in between, composed of our octet and truncated octahedron unit cells. So at the top, you can see the computational result, and at the bottom, the manufactured result that's 14.5 centimeters tall by 12 centimeters wide. Now I have some close-up images of the transition region so you can see what's happening. So here we have the transition between the truncated octahedron and the octet. And we're looking straight on at this front face, corresponds here, right? And you can see that the transition is happening somewhere here. Then we have the transition between the octet and the face X. And in this case, we're looking straight on at this edge. So if you look at this edge and you see this diamond around the edge, that corresponds to this diamond here. And then in this case, we have this edge, diamond around the edge with a bar in the middle. That corresponds to this diamond with a bar in the middle. Here we have the transition between the truncated octahedron and the face X. The transition is happening somewhere here. And then between the solid and the truncated octahedron. We also designed and manufactured an Eiffel Tower inspired structure. So here we have the computational result, the manufactured result. And this thing is 26 centimeters tall. So that's twice the height that our 3D printer can handle. And so we actually printed this part in 3 pieces and then assembled it together. And this actually highlights the scalability of our approach. Okay, so what I did here is I sliced my part for a printer twice as big as my 3D printer. And then I divided those slices in pieces and sent them to the printer individually, and then assembled the part afterwards. And what this means is, because of our voxel-based approach, right, we can arbitrarily scale the macrostructure geometry as large as we want and keep the meso-scale features at the resolution of the 3D printer and essentially achieve a really large separation of length scales, of course, given an appropriate manufacturing platform, okay? Now, everything that I've shown so far is related to these truss-based architectures. And these truss architectures do impose some limitations on us, both from the design perspective and the manufacturing perspective. So in the case of design, first notice that all of these lattice-based structures or architectures that I have shown today have cubic symmetries. And that leads to cubic symmetries in their stiffness properties. So for example, this blue material, like I said before, it has high stiffness along the 3 axes. But depending on the stress states in my structure, I may or may not need stiffness in all 3 of those directions, right? I might just need stiffness in one direction. So in that case, I may be making inefficient use of my material by restricting myself to these cubic lattice architectures, right? Additionally, I demonstrated that we can handle connectivity between different types of lattices, right? But each of these transition regions was designed on a case-by-case basis. So if you give me two different lattices, I'm going to have to redesign the interface in order to ensure connectivity, right? Additionally, let's say I just want one architecture, I just want this truncated octahedron, but now I want to let it orient itself throughout my structure. In that case, connectivity between these oriented lattices becomes a nightmare, okay? So there are some real challenges here from both design perspective and the manufacturing perspective when we're using these kind of truss-based lattices. And so recently we've been working with Spinodal architected materials, which are stochastic and non-periodic, and they help us overcome some of these limitations. So Spinodal architected materials are inspired by phase separation of a homogeneous mixture. And you can see here a simulation of that phase separation happening. If we interpret one phase of this phase separation as a solid material and the other phase as void, we essentially arrive at an architected mechanical material. And furthermore, we can approximate one phase of that phase separation using a Gaussian random field, or essentially a phase field. Okay, so we now have a phase field representation of one phase in that homogeneous phase separation. And then we can use some cutoff and define a level set field that essentially defines our geometry of these solid spinodal architected materials. Now, as you can see, we can also control some parameters, right? So here we have a parameter kappa that enables us to control the spinodal feature size. So you can see with increasing kappa, the feature size reduces of our spinodal materials from left to right. We can also control the density of our spinodal architecture by controlling rho here. So you can see from top to bottom, density of the architecture increases, okay? But I think the most exciting parameter that we can control is actually this parameter n, the wave vectors. So if I allow my wave vectors to be randomly sampled on a unit sphere, as you see happening here, this is what the geometry associated with those wave vectors looks like. And since they're located randomly on this sphere, I don't have any directional preference. This material is going to essentially end up being isotropic. It's totally random. But if I limit where those wave vectors can show up, if I limit them just to these pink regions, now you can see that I'm kind of controlling the geometry of the spinodal architecture. You can see some kind of lamellar features showing up. So now clearly there is some directional preference of this spinodal architected material. And of course, there are infinite ways that we could restrict our space of wave vectors. And for our case, topology optimization, we've chosen to restrict our wave vectors in 4 different ways to arrive at 4 different spinodal classes, okay? And we think that these limitations, these wave vector restrictions cover a wide enough range of the design space, especially when we start allowing these architectures to orient themselves, which we'll see in a minute. Okay, so we have our isotropic spinodal architecture that has the same stiffness in all directions. We have a cubic architecture that has higher stiffness along the coordinate axes. We have a lamellar architecture that has higher stiffness in a single plane, and then a columnar architecture that has higher stiffness along one axis, okay? And so now, when I go to topology optimization, I don't need to change anything with respect to what I showed you before, right? I just, instead of truss lattices, now my candidates are these spinodal architectures. And so I can use the same design variable field to select from the different spinodal architectures. But we are going to introduce some additional complexity or some additional design freedom here. So let's take a look here how the components of our elasticity tensor vary as we vary the density of our spinodal architectures for all 4 of our cases, right? So you can see that we can vary freely in a range between 0.3 and 0.7. These limits are based on manufacturability limitations. But now we can introduce an additional design variable field that allows the density to vary. Okay, so now we're selecting from these 4 different classes, and then say I choose the columnar. Now I have the freedom to make the columnar vary anywhere between 0.3 and 0.7 density. Okay, we're also going to introduce some orientation design variables so that we can arbitrarily orient these spinodal architectures throughout our structure, which provides significant design freedom, as you'll see in a minute. Now, you may be wondering, what's different here? Before I said with the lattices, if we allow them to arbitrarily orient, connectivity becomes really challenging. And that's actually one of the key features of the spinodal architectures. Because they're stochastic and because of this phase field representation that we have, we can easily interpolate between them and ensure well-connected interfaces, no matter which spinodal classes you're connecting, which spinodal densities you're connecting, which spinodal orientations you're connecting. Okay, so if I have a phase field representing each of my spinodal architectures throughout my structure, so I have a phase field for isotropic, a phase field for cubic, a phase field for lamellar, columnar, then I can use this equation to interpolate between them. And this equation kind of looks complicated, but it's illustrated here, where I'm trying to interpolate a transition region between the lamellar and the columnar architectures. And you can see that we can use this parameter R-phi to sort of control the length scale of that transition. And we end up with a well-connected transition between these different architectures. And because the architectures are stochastic, the features that show up in the transition region are totally valid. Okay. Another thing that I want to point out here is, now that we've interpolated our phase fields of the different spinodal architectures to achieve a single phase field over our entire structure, now, as before, we can generate a level set field based on some density value. And now we have a function that essentially tells us at each point or at each voxel in our domain, whether we have solid material or void material. And so now I have a voxel representation, and so I can communicate again with my 3D printer using this voxel representation, just like we did with the lattices. Okay, so no need for STLs here either. So just to summarize, here's the spinodal topology optimization formulation. Again, it looks very similar to what we had before, except that we've introduced several new design variable fields that provide additional design freedom to achieve potentially more optimal solutions. And just for completeness, let me also mention that, again, with these porous architectures, we need to account for the relative density. And in the case of the spinodal, that's going to come through the density design variables that we introduced. And then again, we need to interpolate our stiffness. So we're going to use the same interpolation function that we did before to penalize material mixing. But this time, our homogenized elasticity tensor of the spinodal architecture is a function of the relative density and the orientation. Okay, so we pre-compute the homogenized elasticity tensor as a function of relative density, and then during the optimization, we orient that stiffness elasticity tensor to get an oriented tensor, and then we interpolate the oriented tensor. Okay, so let's look at a couple of quick examples. Here's that cantilever beam again. So we're limiting, in this case, we're limiting the volume to 5% of the domain volume. And first thing to notice is all 4 of these spinodal architectures are available during the optimization, okay? But the optimization chooses to select just the columnar, okay? And if you look here, you can see these red lines are flow lines through our structure that are indicating the direction of the stiff axis of that columnar architecture. So what the optimization has done is it has kind of realized that it's more efficient to use just the columnar architecture and orient it locally to be aligned with the principal stress trajectories of our structure, or kind of aligned with these sort of truss-like members, okay? So that's one thing. The other thing I want to point out here is, remember for the lattices, when we compared the lattice structures to the reference solid isotropic case, we could never do better with the lattices in terms of stiffness than we did with the reference. Here, remember, so F0 is the objective function value of a solution that is made of a solid isotropic material. In this case, F over F0 less than 1 indicates that our spinodal design actually does better than the solid isotropic design. And this is not trivial. We could not do that with the lattices that had a fixed density and a fixed orientation. But now, because we allow for the orientation and we allow the density to vary, we can actually do better than the solid isotropic solution. So here we're allowing the density to vary between 0.3 and 0.7. I can also control my density if I want to. So in this case, I'm saying density has to be 0.3 everywhere. And so of course I've sacrificed my objective function by doing that. So now I'm not performing better than my solid isotropic solution. But there may be some reasons or some applications where this is desirable, right? So we sacrifice the stiffness of our structure to gain some control over the porosity. So an example where that might be useful is in the case of bone replacements. So here again, we're designing this craniofacial implant for a patient that's had a traumatic facial injury. And so the design domain is based on the geometry, specific geometry of that patient's face. We have some support conditions, loading conditions, and we want to design a scaffold or a bone replacement that both takes the mechanical load, but also potentially allows for regeneration and regrowth of the actual bone material. And so here is a case where we may be okay with sacrificing the stiffness of our structure a little bit in order to control the porosity, okay? And so I just have one design that we obtained using that design domain from the previous slide. So here you can see the craniofacial implant, the computational result, which used both the columnar and the lamellar architectures, and then the manufactured result, which is printed at real scale. And I will stop there, and I will be happy to answer questions. Thank you.
Okay, thank you very much, Professor Sanders, for your so fantastic talk. So now we are in the Q&A session. So I wonder from the audience if you have any questions.